The next concept that I would like to bring to you, we've spoken about stability of isotopes. Now, we have seen that these are isotopes. Yes, these are nuclide, these are nuclide. Both of them are isotopes because they've got the same atomic number but different mass numbers. Now, we said that a nuclide can either be stable or unstable. 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 When you talk about stability, stability is assessed by a neutron-proton ratio. Neutron-proton ratio. And most stable isotopes have a neutron proton ratio of 1:1. Most stable isotopes will have a neutron proton ratio of 1:1. Let us look at an example. Look at calcium, which is atomic number 20 and has a mass number of 40. From this nuclide, because it is a nuclide, you can be able to see the number of protons are 20. And then from mass number, we say that mass number is the sum of the number of protons and neutrons. Therefore, you can take 40 minus 20 to get the number of neutrons. So number of neutrons here are 20. Therefore, our neutron-proton ratio in calcium 40 is 20:20, and this translates into 1:1. So this is a very stable nuclide. So we are saying that most stable nuclides will have a neutron-proton ratio of 1:1. However, as the atomic number increases from 20, the neutron-proton ratio increases progressively up to 1.6:1. So, and this is a ratio now, neutron-proton ratio of 1.6:1. We still say that this ratio is still within the stability region. This is still within the stability region. Still within the stability region. But above this ratio, 1.7 going upwards, above that ratio, the nuclide becomes too large. Because you can see now, when you're talking about 1.6:1, this is neutron-proton ratio. It means it has got more neutrons than protons. So above this ratio, neutrons will be so many, and the nuclide becomes too large and therefore unstable. So above the ratio 1.6:1, above the ratio above the ratio 1.6:1, the nuclide becomes too large or too big and therefore unstable. So if you want to identify an unstable nuclide, you just go and get the number of neutrons, the number of protons, get the ratio. If the ratio is above 1.6:1, then that nuclide is automatically unstable. So anything that's above here, it is unstable. And you can be able to illustrate the stability of nuclides using a graph, or rather a diagram. Let's see how we can be able to illustrate that using a graph. Just put our scale. This may not be very accurate because you can see I'm doing it on a whiteboard, but it's going to bring home the point. So 20, 40, 60, 80, 120, 20, 40, 60, 80, side we are going to have the number of neutrons. We're going to have number of neutrons. Here we're going to have number of protons. And that line, it indicates a neutron proton ratio of 1. A neutron over proton is 1. That is 1:1 along that line. So we've looked at calcium with 40 neutrons, and it is in atomic number 20. So you'll find that above, we are saying that as the atomic number increases, the neutron proton ratio increases progressively up to 1.6. Above that, the nuclide becomes unstable. So we expect number of protons indicates the atomic number. As it increases, anything that is above here becomes unstable. So you even come here and show some. As I said, Lana, this may not be very accurate, but you can do it from your book. I just want to explain. Look at this. Anything that is inside here, stable isotopes lie within the shaded region or the shaded area. Anything that is within here will have a ratio of not more than 1.6:1. All those ratios will lie in between here, and therefore we say that those isotopes are stable. Above here, you'd find that those isotopes that are here have a ratio above 1.6:1, and therefore they are unstable. As we shall come to see later on, they are going to break, or rather they are going to undergo some changes and will emit some particles called alpha particles. All these that are in this particular point, and you can be able to see, if you are to take any line here, probably a point like this, you'll find that 120 neutrons, and maybe something like 100, or maybe in between 80 and 90, or maybe you can even take 80. You'd find that ratio would be more than 1.6:1, and therefore this particular region will have unstable nuclides. All those nuclides that are here, we'd have, you'll find that it is around 140, and maybe 20. That's a point. So a point there, you would have 140 neutron, maybe 20. You'll find that even if you are to get the ratio, and this is just an example, this will be 1 and this will be 7. This is a very high ratio, which is actually unstable. This is unstable. This will be unstable nuclide. So this is just an explanation that any point that lies in between here will have a ratio above 1.6:1, and therefore unstable nuclide. All these nuclides will undergo some changes and will emit some particles called beta particles. This is just an illustration of what you've just learned. So along this line, we have a neutron proton ratio of 1:1, neutron proton ratio of 1:1. And we see that any element that has got a neutron proton ratio of 1:1 is a stable nuclide. But above this ratio, again, we say it is unstable. Now, let's proceed. So we've said that a nuclide can either be stable or unstable. And when I say now stable, you're able to identify how are you able to get a stable isotope, and you're going to use their neutron proton ratio. Now, for those unstable nuclides, they undergo some changes. Unstable nuclides undergo some changes. Unstable nuclides undergo some changes. Unstable nuclides undergo some changes by emitting radiation, or rather by emitting radiation in form of particles and energy. By emitting radiations in form of particles and energy. So these unstable nuclides are going to undergo some changes. In that process, they're going to emit some radiations, and these radiations will be in form of particles, which shall come to see what type of particles are emitted, and energy. Now, the process by which unstable nuclide breaks up to yield a different nuclide of a different composition with emission of radiation and energy, that process is called radioactivity. This process is called radioactivity. So you're saying this is the process. This is the process by which unstable nuclide breaks up and yields a new nuclide with different composition and accompanied with emission of radiations and energy. We say radiations are emitted in form of particles. So the process by which unstable nuclide breaks up to yield a new nuclide. So it will break. So talking about unstable breaking to yield a new nuclide with different composition, with emission of radiation and energy. That process is called radioactivity. When you talk about different composition, what do we mean? Talk about different composition. We say that a particular nucleus characterized by its protons and neutrons is called a nuclide. Now, we are having a new nuclide with different composition. It is different from the previous one, from the one that was unstable. So it will be different in terms of either in terms of either one, atomic number, that is the number of protons, or two, mass number. Now, obviously, when you say mass number, it means the neutrons have been affected. So, unstable nuclide breaks up to yield a new nuclide. This new nuclide will be different. One, either in terms of atomic number or in terms of mass number. And mass number affect the number of neutrons. That is what we say with different composition. That's called radioactivity. And all the substances that undergo radioactivity are called radioactive substances. So radioactive substances are substances that undergo radioactivity. Substances that undergo radioactivity are called radioactive substances. And then still, those isotopes, now we say isotopes are atoms of the same element with different mass number. Those isotopes which are radioactive or undergo radioactivity are called radioisotopes. Radioisotopes, these are radioactive isotopes. The one that can break up to yield a different nuclide are called radioisotopes. Now, There is another term I want us to look at, and that term is radioactive decay. When you say something is radioactive, it has a capability of spontaneously splitting. When I say spontaneously splitting, I mean without external stimulus. So, spontaneous splitting. So, anything that is radioactive has a capability to spontaneously disintegrate, or rather to spontaneously break up. So, the spontaneous disintegration of a radioactive nuclide, So a radioactive nuclide is the one that undergoes radioactivity. Spontaneous disintegration of a radioactive nuclide is called radioactive decay. It is referred to as radioactive decay. Very important term. The spontaneous. When you say spontaneous, we mean without any influence from external factors, without external stimulus. So it is splitting by itself. That process by which a radioactive nuclide splits by itself spontaneously is called radioactive decay. Now, having looked at those terms, it is important for you to note that radioactivity is therefore a nuclear process and not a chemical process. So radioactivity is a nuclear process, and not a chemical process,